All right. Um, this is a little supplemental lecture because we didn't get to it in class. Um, and again, I think these are going to be useful ideas, especially if you're going to do quantitative work um, in a thesis that you write. However, I think they're a little bit second order sometimes for understanding exactly what's going on statistically and engaging with things like p-values and confidence intervals. So if you are less going to be less engaged with quantitative analyses yourself in the future, you can maybe focus on other parts of the content of this course, although I still think this stuff is useful and interesting. So we're going to be talking about what are sometimes called non-parametric tests, generally called non-parametric tests, but I think should actually be called exact tests, though I will sort of use both names here. So let's talk about what we mean when we say exact or non-parametric tests. And this is related to sampling distributions. So we've engaged with two different types of sampling distributions in this class. When we started talking about sampling distributions, we looked at one sample test of proportions, and we related everything to coin flipping, right? We said, imagine, in a simple example, you have a coin, you flip it 100 times, and you observe 75 heads. Do we believe that this coin is fair or not? And we looked at the sampling distribution of the proportion of heads out of 100 flips when the probability of flipping heads for the coin was 50%, right? And we simulated to get that sampling distribution, or could alternatively have just calculated that as opposed to simulating for it. But in this case, I'm going to say, exactly characterize the sampling distribution, right? If we flip enough coins enough times, we will be able to see a histogram of the sampling distribution for the proportion of heads out of 100 flips when the probability of heads is 50%. So I'm going to call these exact sampling distributions when we know everything we need to calculate the sampling distribution. The other thing we did, moving down to the blue text now, is we have also engaged with sampling distributions using the central limit theorem. And I'm going to call these approximate sampling distributions. And remember, there was this long lecture here where we said, okay, for things like the t-test, we look at the sample mean and we say, we don't really know the distribution of the sample mean, but it's roughly normally distributed around the true mean of the population. And we can understand the spread of that sampling distribution by engaging with the standard deviation. Now, we don't have to revisit that whole discussion. As we'll recall, we talked about that briefly, and then we often just went into engaging with software to calculate p-values and confidence intervals using those sampling distributions, and didn't go too much into the nuts and bolts of the sampling distributions themselves, because it got very complicated when we were using these so-called approximate sampling distributions based on the central limit theorem. The key point, though, is when we were using approximate sampling distributions, we had to engage with a statement like this. We had to say, these t-tests, the p-values from these t-tests, the confidence intervals from these t-tests, are only accurate if we have enough samples for the central limit theorem to kick in, right? If you run a t-test, you need, I think, 30 or more, some people say 20 or more samples, but you can't really run a t-test well with 10 samples. If you do, the p-value that you get is not going to be accurate, right? Because it's using this approximation to the sampling distribution that is not a good approximation. So again, this is the split between exact sampling distributions, which we have rarely looked at, only in the very beginning of this class, and then these approximate sampling distributions that we let R deal with under the hood, but we know they're there, and sometimes we are a little bit worried that we don't really have enough observations to support the use of an approximate sampling distribution, meaning we shouldn't really be running, for example, a t-test when we only have 10 observations, or a two-sample prop test when we only have, 10 observations per group. In both of those cases, if you try to submit that in a manuscript, often the reviews will come back and say, you can't use these t-tests. They're sometimes called parametric tests or asymptotic tests. You need to use an exact test. So what we're going to talk about now is alternatives to these tests when we have a small number of observations. So again, when we have 30, fewer than 20 maybe samples, things like t-tests or chi-square tests may give us inaccurate results. And so instead, there are methods that give exact results, exact p-values, exact confidence intervals sometimes, with fewer observations. Again, these are sometimes often known as non-parametric tests. I think that's sort of imprecise, so I call them exact tests, and that's also a name used in the literature. So we're going to talk about 3 exact tests for now. There are others that we will engage with some in the future. And we're going to talk about them, rather than starting with the names of the tests, we're going to talk about them for the different types of problems we've engaged with. Right? So we've engaged first with 2-sample binary outcome problems. And this is like a binary exposure and a binary outcome. We can think of it in that way as well. And we've looked at contingency tables for evaluating this. Often we're, again, evaluating an association between an exposure and an outcome, or a difference between probabilities of an outcome in 2 different groups. Those are equivalent. Via a contingency table. Often we run that test as a chi-square test. The next thing we're going to look at is 1-sample problems with continuous outcome. We don't really engage with these in practice so much, but we did talk about them once upon a time. And here, when we've looked at them before, maybe we measure the heights of 100 people and would like to know something like the average height of people in the population based on our sample of 100 people. Or we'd like to test if the average height is some pre-specified height in the population based on our sample. And so we'll see how to use a non-parametric test there. And then the final place where we use this are so-called 2-sample continuous outcome problems. You can also think of this as a problem where you have a binary exposure and a continuous outcome, and you want to look at the association there. We've generally used 2-sample t-tests here to look to see if the means of the 2 groups are different. And we'll see alternative approaches there. So again, for now, we're going to just start with this, engaging with the contingency table using an exact test. And here, we actually already talked about the test. It's sometimes called Fisher's exact test. And we noted that there's this difference. There's a chi-square test that is maybe most common for us to see, or most traditional. And then there's this Fisher's exact test, and they're very, very similar, except, again, remember I said they use 2 slightly different ways of calculating the sampling distribution of our statistic under the null. The chi-square test uses an approximate way of calculating the sampling distribution. The Fisher's exact test is more computationally intensive, but exactly calculates that sampling distribution. So this is just a complicated way of saying the p-values out of the Fisher's exact test are exact p-values. The p-values out of the chi-square test are approximate p-values. And you'll remember, if you run that chi-square.test in R, every now and again it gives you some warning saying, hey, something like your sample size is too small. You shouldn't be running this. So in general, there's not really a downside to using the Fisher's exact test as compared to the chi-square test. I think, again, that's sort of my go-to now. Classically, historically, the chi-square test was used, especially before we had computers for doing statistical tests for us, because the chi-square test is pretty quick to calculate by hand. The exact test would take an enormous amount of time to calculate by hand for a number of these problems. So again, computing has changed things, but I would say Fisher's exact test is generally a better way to go. You lose almost nothing by using it. And the chi-square test is more common because, for people trained in like the 1960s, when computing was, not nearly as accessible or as fast, chi-square tests were the standard. All right. So that was going with a binary exposure, binary outcome. Now let's think about where we don't have this exposure outcome way of engaging with things. We just measure, one continuous numeric variable on a bunch of people. And before, we've talked about using t-tests there to try to test if the mean is some fixed value, right? We look at the height of 100 people randomly sampled from our population, and we want to test if the mean height in the population is some pre-specified value, and we compare the mean height in our sample to that. And again, a t-test will do that and help us form a confidence interval for the mean height in our population. The analog here, the two analogous tests are known as the sign test and the Wilcoxon signed rank test. And both of these, rather than testing if the mean of the population is a pre-specified value, they test if the median of the distribution is a pre-specified value, which is slightly different. It turns out somehow it's simpler to engage with the median here than the mean. So, that's one downside. If you were interested in the mean, now if you want to use these non-parametric tests, you kind of have to engage with the median instead. On the upside, they don't rely on the central limit theorem, as we mentioned before. They don't rely on this, and they can be used even if you have only a small number of observations. Right? The p-values you get out of them will be accurate. They're not these approximate p-values. Will be accurate even if you only have 10 or 15 observations. Again, now you're testing the median rather than the mean. And I'm not going to go into a ton of details on exactly what these tests are doing. I'll talk a little bit more in the next slide about it. I just want mostly to note that these are alternatives that allow you to test if the median is a pre-specified value and can give you things like confidence intervals for the median. So let's just talk a little bit about what the sign test is doing first. So the sign test, let's imagine we posit that the median height, we believe the median height in the population is maybe, I don't know, I'm going to make something up, 5 feet 10 inches. We look at our sample and we say, okay, our null hypothesis is the median height is 5 feet 10 inches. Let's look at the proportion of people in our sample who have a height above 5 feet 10 inches and the proportion who have a height below 5 feet 10 inches. And we say, if in truth that is the median in our population, then for each person there's a 50% chance they have a height above the median and a height below the median. And so we can compare the proportion in our sample to that 50%. And see if it is significantly different from 50%. And if it is significantly different from 50%, say in our sample, only 20% of people have a height over 5 feet 10 inches, right? Then we would say, oh, in our sample of 100 people, only 20% have a height bigger than this. That is statistically significantly different from the 50% we would have expected if this was the population median. So we could then potentially reject that null hypothesis that says the population median is 5 feet 10 inches. So again, the details on that are not super important. I think it's interesting, and it's actually a relatively simple test that we have engaged with at various points without calling it the sign test in our class. So that's one way, again, where you don't have to use the central limit theorem and can either test if the median is a pre-specified value or find a confidence interval for the median. The Wilcoxon signed rank test modifies this sign test a bit, and rather than just looking at the sort of proportion of observations that are above or below the median, also tries to engage with the magnitude of those observations. Do the observations that are particularly large or small in magnitude tend to lie, particularly, I should say, different from the median, tend to lie above the median or below the median. Again, the details are not so important. I think understanding the sign test can be helpful as, again, it relates what we're doing back to coin flipping. There's not really a precise rule on whether one of these is better than the other. I think in practice, people tend to use this Wilcoxon signed rank test as opposed to the sign test, but it's not necessarily better. And I guess the last piece I would say is, engaging with one sample test is much rarer than engaging with 2 sample tests. So this is not that common a problem to engage with anyways. All right. So, okay, now the last piece is here we have 2 groups, and we have continuous measurements in those 2 groups, and we are interested in identifying, classically, when we talk about a t-test, we're interested in identifying if the mean in one group is larger or smaller than the mean in the other, or if the 2 means are identical. Here, we're actually going to engage with something slightly different. Our null hypothesis is not just that the means are the same in the 2 groups. Our new null hypothesis for this non-parametric or exact test is that the distribution of the outcome in both groups is identical. This is a little bit stronger than just saying that the means in the 2 groups are the same. So again, under the null hypothesis, the two groups, the distribution of outcome in the two groups is identical. And the test that we use here is either known as the Mann-Whitney U-test or the wilcoxon rank sum test. And actually, these two tests are equivalent. They are posed slightly differently if you look at them in the literature or look at them up on Wikipedia, but they end up doing something identical. And so again, really what they try to engage with is, do we have evidence that in general observations from group 1 tend to be larger than observations from group 2 or tend to be smaller than observations from group 2? And if we have evidence of either of those, then that would give us evidence against the null hypothesis that the distribution of outcome in both groups is identical. So again, this is a way of testing for difference between two groups. And I'm going to talk a little bit about what it does under the hood. You don't need to worry too much about that. Primarily, I think the main takeaway here is if you want to run a t-test between two groups and you don't have enough observations in order for the central limit theorem to be justified and those approximate p-values to be reasonable or good, in that case you can use this Mann-Whitney U-test or wilcoxon rank sum test and get a test trying to identify if there's a difference between the two groups that is valid even for a small number of samples. So let's again talk about this Mann-Whitney U-test. We're going to talk about the way that it is posed under this name. So what this test does under the hood is it looks at all the observations in group 1 and it compares each of them to each observation in group 2. So let's imagine we have 5 observations in group 1 and 10 observations in group 2. It takes the first observation in group 1 and compares it to each of the 10 observations in group 2. It then takes the second observation in group 1 and compares it to each observation in group 2. And it goes through and does this with all the observations in group 1. So at the end of that process, we would have 5 times 10, we would have 50 comparisons. And if n1 and n2 are the number of observations in group 1 and group 2, then we would have, in general, n1 times n2 comparisons. And by compare, I mean, it looks at each observation in group 1 and group 2 and identifies which one is larger. Does that favor group 1? Is the observation in group 1 larger? Or does it favor group 2? Is the observation in group 2 larger? Now, if the observations in group 1 and group 2 come from the same distribution, then in roughly 50% of those comparisons, the observation from group 1 should be larger, and in roughly 50% of those comparisons, the observation from group 2 should be larger. If, when we do this, we find 90% of the time the observation from group 1 is bigger than the observation from group 2, then that really gives us evidence that group 1 and group 2 don't come from the same distribution, and observations in group 1 tend to be larger than observations in group 2. Right? So the way the Mann-Whitney test works is, it does this calculation. It looks at the proportion of times that comparison, say, favors group 1, that the observation from group 1 is larger, and then it identifies if that is statistically significantly different from 50%. Right? It may be 51% of the time group 1 is favored, but that's well within what we might expect if the two observations came from the same distribution. Again, it depends. It does all that calculation under the hood to understand what we might expect under the null versus what we might not expect. And then, again, it tests that null hypothesis, and it can tell us if, again, at the whatever pre-specified alpha level, say 0.05, it can tell us if at that level it can either reject the null hypothesis and can see evidence that the two are different, or if it cannot reject that null hypothesis and doesn't have evidence that observations from the two groups come from different distributions. So again, big picture takeaway is that this is an alternate approach that you can use when you want to run a two-sample t-test, but you can't because you don't have enough observations, right? It's maybe not perfect. It's testing a slightly different null hypothesis than that t-test is testing. It's testing that the observations come from the same distribution rather than just that the means are the same. But it can be a very useful approach in some of those cases. So one thing to note is you can actually have a funny situation where observations in group 1, the distribution for observations in group 1 has a larger mean, But group 2 generally has larger values. For example, if we're looking at income, in group 1, in the population has some enormous values and many really small values. In group 2 tends to have, large but not outlyingly large values. Then it could be that the Mann-Whitney test would show that group 2 tended to have larger values than group 1, but testing a difference of means would say that group 1 has a larger mean than group 2. And again, this can happen. And part of it is because the two are sort of evaluating different things. It's kind of like how, you could have two distributions. One could have a larger mean than the other, but the other could have a larger median, right? You can have funny things like that if you have issues with tail behavior, if you have some large, essentially outlying values. So a big picture summarizing this. So exact tests are generally used when we have small sample sizes. Exact tests are sometimes, again, called non-parametric tests. They're often used when we have small sample sizes. They generally test a slightly different null hypothesis than the t-test, or than the equivalent, what's called a parametric test. This is not the case with the Fisher exact test versus the chi-square test. Those test identical things. But again, these like sign test versus the t-test, Mann-Whitney test versus the t-test, those test slightly different null hypotheses. Often you don't really get confidence intervals when you use them. You can sometimes, but not always, which is a little unfortunate because confidence intervals can be quite useful for scientific conclusions. Again, I don't think that they are of first order importance in this class, but if you are analyzing data, you may have to use them if you have a small sample size, and you may run into papers where they discuss, because we had a small sample size, we used a Mann-Whitney test rather than a t-test, and here are our p-values, and it's worth sort of noting what is going on there. Yeah, I guess the one last piece I would say is, if you have a very small number of observations in your study, ideally, you're not in an ideal place, period, not just because you have to use one of these non-parametric or exact tests, but also because you're going to have a lot of uncertainty in your result, right? You have 10 observations in your study, there's a lot of uncertainty, and so maybe, ideally, one would have planned a larger sample size. I guess I feel like when we are reduced to using non-parametric tests, often it means that, statistics is not really what we want to engage with. One can do, obviously, case studies can be incredibly important with small numbers of observations, but probably we shouldn't really think we can draw generalizable conclusions from such a small number of samples unless we have an incredibly clear difference or incredibly clear clinical result. Great. Thank you much.